Hey, good afternoon, crispy brownies. How are you doing on this Monday? A bit worried about midterm results. Was it was it a difficult exam for you? I want to ask people in general today about how they feel about it. Yeah, not fun, very lengthy. Just a bit longer than expected. Gotcha, gotcha. How long did it take you guys to work through the exam? Mega Mike thinks it was fine. Probably in total like 3.5, 4 hours. Is that what it was like for the rest of you? Slowly churned through it in like 4 hours. Minus the distractions and goofing off, I think like 6 to 8 hours. You were checking everything constantly to make sure it didn't have any missteps. Around 6. Gotcha. Yeah, maybe a little long. 4 to 5 hours. Had career fair mid-exam. Slow and steady for... Oh, for a second I read that as 3/4 of an hour. I was like, that's pretty fast. That's pretty fast, Tim. No, but I got you. 3 or 4 hours. You know, I think for like a take-home exam, 4 hours of like, you know, focusing, just getting through it. I think that's reasonable. I think at our review session, I was thinking more 2 hours, but I mean, really, I think that was that was too fast of an estimate. But you know, on a take-home exam, you can. I think usually we slow things down a little bit because you want to take more time and check everything. I think it took me that long because I was checking all the notes for a lead because I got stuck. Yeah. I mean, that probably what happened to a lot of you for a lot of the time. It's probably like there were maybe 1 or 2 problems where there's something that really gets you stuck, and then it takes a long time to just figure out that one thing. On an in-class exam, sometimes that can happen, but then you end up just having to skip that part. I spent extra time double checking everything. Yeah. Which is good. Well, okay, by the time you guys got to the end of the exam, do you feel like... Yeah, I feel like I feel pretty confident about my answers, or did you still feel like, man, I have no idea what it was asking? I mean, I definitely say it was challenging. I would say that's a challenging exam. And I certainly expect many or most students to feel challenged by a couple of those problems. I felt okay except 2 of the longer questions. I knew what it was asking, I just wasn't sure if my method was valid. Gotcha. Gotcha. A couple of the short response, but ended up getting them all. The instant grading there was a plus. Gotcha. So for true or false, you guys saw if it was correct or incorrect right away. Is that what you're saying, Tim? Oh, a couple of the short responses were tricky. Yeah. You know, yeah. Yeah, I think it was difficult. Doable, but I mean challenging. When I'm reflecting back on the exam, I think part of it, please keep the subsequent exams at 24 hours. Yeah, definitely. I don't like the idea of saying you only get an hour or 2 hours because I also know you guys have different schedules. Some people need to work, or they might have some obligations on the weekend. So, I mean, thank you for setting aside that weekend day to do this, because I know that's not the way you'd prefer to spend Saturday. Let's just say that. But I think when Dr. Lagore and I reflected back on the exam, we were, because we met this morning, we were like, there was a couple questions if we could go back, we would have worded those in a different way to make it a little clearer. Because we got plenty of questions that I think are mostly concerning just the language of the problem. Vinny says, definitely a fair exam. It was long, but the 24-hour window made it much more doable. Okay, good. Yeah, we'll definitely stick with this model of giving a big time window. You know, take your time. It sounds like most of you spent somewhere between 4 to 6 hours. Got tricked by one of those MC questions. Wait, what's MC? Oh, multiple choice? Wait, was there multiple choice? Oh, true, false? Yeah, some of those true, false are a little... Yeah, some of those are difficult, too. Okay, but I mean, it sounds like most of you feel like, okay, it was hard. Took a little longer than you expected, but it's like, okay, we got through it. And that makes me happy to hear. Maybe less questions that are longer next time. The fact that it was many smaller questions made for lots of checking and double checking. Not a big thing, though. I hear you. I mean, one thing I will say, some of those questions I noticed, they tested the same thing. You know what I mean? So maybe we could have done away with one of those, because it's kind of like you might have done a similar procedure in another problem. So that can also save on time. Yeah. It's a fair exam, just felt a bit unprepared by how many questions there were. I hear you. At least for me, it was mostly the first quarter of the semester I was tested on. Also, some of the questions were so short, I wasn't as confident that I did everything. No, I hear you. I think that speaking to... Yeah, some of the questions are a little longer. And then if a question is shorter, you're like, wait, am I missing something here? I got you. And you be MAE student, I do agree that I think the content was more front-loaded. I mean, in terms of content from the semester. Like, there was a lot of kinematics and coordinate transformations. Vinny says, any idea on when grades will come out? I think, trying to be realistic about it, I would probably say end of next week, if I had to guess. I would think end of next week at the latest. That's my guess. Hopefully beginning of next week. That would be ideal. Hey, but kudos to you guys. Thanks for pushing through on a tough class. Flight dynamics is tough. And learning flight dynamics, like really getting it ingrained, I think it takes years, and I don't even feel like I'm there. You know, I feel like you could always improve on this. So you guys are, we're proud of you guys for just pushing through on all this content. Vinny says, is there another exam before the final? Vinny, I think that there's just 2 exams. So there's this midterm, and then we're gonna have a final, but it's gonna be weighted the same as this. So like the way the grade distribution works is it's 20% for the midterm, 20% for our final exam, and 60%, the rest is homework. Yep, you're welcome. Yep, definitely proud of you guys. So keep it up, keep plugging away. School is heavy, the semester is heavy, especially like this time of the semester. Just keep putting one foot in front of the other and we'll make it through. Okay, let us get into the content for today. My prediction is that this will be a shorter lecture because I got like one example I want to get through, and we'll leave it at that. All right. By the way, we're listening to some World of Warcraft tavern music in the background, if any of you are curious. I haven't played World of Warcraft because I think I would get too into it, but I love the music. There are certain games I avoid because it's just dangerous. Let's be honest. Okay. Last time, we derived... It sounds like a jungle safari. Yeah, I know. I love it. Let's back it off a little bit, though. Turn it down a little bit. Okay, so we derived these longitudinal equations, and let me go down to those to just remind you, because we organized them in this state space form. Okay. So this state space model with 4 states, 2 inputs, this is our longitudinal flight dynamics. And today we're going to talk a little bit about stability derivatives. And stability derivatives are these partials in here. Some of them are with respect to forces, some of them are with respect to moments. And in order to analyze the dynamics of a specific aircraft, whether it's an F-16, a Boeing 747, we need to know what to plug in for these values. Okay, so yeah, longitudinal flight dynamics equations. So these are the linear perturbation dynamics of the aircraft about the following flight condition. So this is what the longitudinal dynamics pertains to. So it's steady, it's level, it's wings level, it's non-turning, and it's coordinated. Coordinated flight. So what this flight condition means, if you're trying to visualize it, it's flying straight as an arrow at constant altitude. That's basically what it is. Probably the simplest reference flight condition. So when we were deriving the linearized dynamics, we found 4 interdependent perturbation states. And these depended on 2 perturbation inputs. So let's list those right here. So this is the longitudinal perturbation state vector. And this is the longitudinal perturbation input vector. So what are these perturbations in? Well, delta U, delta W. So these are 2 of our velocity states with respect to the body frame. Delta Q, that's a perturbation of our pitch rate. And delta theta is a perturbation in our pitch angle. So those are our 4 perturbation states. And then we have 2 perturbation inputs, which are changes in our throttle and changes in our elevator angle. And because these states are interdependent and they don't depend on any other possible aircraft states, these inputs and states are sufficient for describing an aircraft moving about the described reference flight condition, which is just flying straight as an arrow, basically. So as we linearized, we encountered stability derivatives. We pointed those out on the other page. Those are those partial derivatives. So these are the partial derivatives of forces and moments, and they're partials with respect to our states and inputs, and then they're divided by some mass or inertia term. So let's give an example. And this is the stability derivative that we will work with today. So this stability derivative, x subscript u, is 1 over m dx du. And this partial is evaluated at the reference flight condition. That's what I mean by this star. At reference flight condition. And so if you look at the units of this really quick, you know, mass is kilograms. This is a force. X is a force, so let's say newtons. And then U is a speed, so let's just say meters per second. And newtons is equal to kilograms times meters per second squared. So a mass times an acceleration is a newton. So overall, the units of this, you have kilograms times meters per second squared divided by kilograms times meters per second. So the units of this are, it's 1/second. And this has a corresponding dimensionless stability derivative, and we're going to derive this in the example below. So we're going to get an expression for this. All right. So let's just get into an example. We're going to blast through this. And once we're done with this, we're done. So we're going to get out of class early today. That's what I expect. Okay, so this example is, it's going to focus on these terms. What do they mean? Where do they come from? And so let's get right into it. So we're going to use this following reference flight condition, and it's the same one we listed up above. So flying straight as an arrow. So we analyzed this reference flight condition before, and we found some constraints on the translational dynamics. I'm going to show you these constraint equations right here. So let's break this down. I know there's a lot right here. So let's look at this first. These are forces acting on the CG, and it's in body frame components. And you can see that from the B subscript over there. Okay, I want to introduce an important notational change that I wish I could go back in the past and change earlier. So, and the notational change has to do with these variables. You're going to see a subscript A on these. And that's new. When I've written these variables before, we've just put X, Y, and Z. So why am I putting an A here? Okay, because, and it has to mostly do with this X variable. I'm finding that the majority of the textbooks that I'm looking at, and this is going to be important when it comes to stability derivatives, what they like to do is take the thrust and this aerodynamic force, and that's why I'm putting A. X, Y, and Z we've called the aerodynamic force in the X, Y, and Z directions. But they like to combine these and by definition call it X. So, wait, let's do it this way. So in other words, they like to define capital X as the thrust plus the aerodynamic force. So this is a redefinition of what we've called X so far in this course. And so what I would like to do, I wish I could go back to all our previous notes, and every time that we put X, the aerodynamic force, I want to replace it with X sub A. So I might update the notes and post new ones where X is now X sub A. And like I said, the reason I'm doing this is because most textbooks actually do it this way. And a lot of these stability derivatives that we're going to derive, they're found in tables in these textbooks. Like, we don't derive them from scratch most of the time. Like, we're going to derive this one from scratch, But most of the time you just go to a table and you look it up. And so it's going to be important that the notation is consistent. So that's why I'm, at this point, worried about making this look a little bit more like a textbook. Okay? So that's the notational change. All right, what do I have going on this side? Oh, so before moving on, the constraint here is that these forces are all equal to 0. And that's necessary for steady flight. And actually, you see over here, I have that again, whatever. So that's the constraint. These forces, they're all equal to 0. So what I have here, we had this constraint. What are these? These are forces acting on the CG, but it's in wind frame components. So, as you can see here, well, the constraint was that those are equal to 0. But what I'm doing here is I'm multiplying these forces in the wind frame by a rotation matrix, and this is the rotation matrix from the wind frame to the body frame. So by combining these two terms, I'm projecting forces onto the body frame. So the reason that I'm doing this is I want to be able to equate some of these wind frame terms like drag, lift. I want to be able to equate them with some of these common body frame terms like thrust and aerodynamic force. So I want to see the relationship there, and it's actually going to result in a pretty simple expression for this reference flight condition. So we just want to equate these things, and some results going to come out of this. But let's simplify this a little bit, because for this reference flight condition, some things happen. So, for example, at this reference flight condition, the pitch angle is equal to the angle of attack. This is when your altitude is constant. So if h dot is equal to 0, that means that these angles have to be constant. So this is going to go to 0, this is going to go to 0. And so this whole term is going to go to 0 because we're taking sine of 0. And Professor, why are there asterisks on the angles? Okay, what the asterisk means is evaluated at reference flight condition. That's what it means. Okay, so this cosine, that's going to go to 1. Yeah, you're welcome, Shamik. And what else? Can I simplify anything else? Oh, this side force is going to be 0. This aerodynamic force in the y direction is going to be 0. And I think that's basically it. Oh, this rotation matrix, this is already accounting for the side slip being 0. The side slip being 0 is called coordinated flight. So anytime you see coordinated in your reference flight condition, that means wherever you see beta, it's going to be set equal to 0. So that simplified our rotation matrix. Okay. So we have this, and I want to equate some terms. So I want to multiply out the first row. And so that's what I've done here. I took the first row up here, and you see that same term appears here. And then if I multiply out the first row of this, If I multiply out the first row of this matrix with this vector, I'm going to have cosine of the angle of attack times this whole term. And then I'm going to have this minus sine term multiplied with this whole term at the bottom. And so I get this relationship. And so let's simplify this out. And you're going to see a pretty simple equation comes out of this. Now remember, from now on in the class, I'm going to have a new notation where the thrust plus this aerodynamic force, which we used to just call it x, now I'm going to call it xa. We're going to define a new variable x, which is the thrust and the aerodynamic force combined, because that's just convention. All right. Why are we considering only components of W in this and not including components of U? Is there an intuitive reason, or is it just how the math comes out in this equation? Why are we only considering components of W and not including components of U? Wait, what do you mean? Like, little w is the velocity in the BZ direction, right? And U is velocity in the BX direction. Yeah, explain that a little bit, because I'm having trouble relating your question to what we're doing right now. Is that a capital W? Oh, yeah, that's the weight. Yeah. This guy, this is weight. No, you're good. Probably you're not the only one wondering that. Whenever these big W's here, that's the weight of the aircraft. Okay. Okay, so let's get into this. Let's gather all the terms on the right that involve the thrust. So the capital T term. So I'm going to have T star. This one, let's see. Wait, why am I doing a square bracket? So this is cosine alpha squared. And then over here, I have minus sine alpha times sine alpha. Well, let's take that as plus sine alpha squared. And we know cosine squared plus sine squared is 1. So this is going to go to 1. All right. So we took care of the thrust terms. Now we got the drag on this side. Minus D cosine alpha. I have this weight term. So minus weight sine alpha. And then I finally have this lift term. So plus lift sine alpha. And I should put a asterisk on the lift. And the asterisk just means at this reference flight condition. So it's whatever it needs to be to maintain straight flight at constant altitude in this case. All right, so another simplification. See this alpha term? For this reference flight condition, we know that alpha is equal to the pitch angle. So angle of attack is equal to pitch in this case. So that means I could replace this term with a theta. And if you look on the left-hand side of this equation, we have this exact same term. So these two terms cancel with each other. And so we're going to end up with a much simpler expression. Actually, I'm going to stick with this kind of blue color there to just remind you that it's both of those terms combined. Okay, so that x star, that'll be equal to the thrust times 1 minus d plus L. Okay. Now I'm going to introduce another assumption here. And you know what? I probably should have made this a part of the reference flight condition at the top. But I think the convention is when we're looking at this stability derivative for this flight condition, they make this assumption that the angle of attack is 0. And if that happens, you can see that you're going to have sine of 0. That's going to go to 0. You're going to have cosine of 0. That's just going to be 1. And you're going to get this. It's thrust minus drag. So we related this force in the body frame to some of these wind frame variables like lift and drag. But because of assumptions that we made, namely the angle of attack being 0, only the drag survived all the way to the end. What a drag. Okay. Now, we're looking at perturbation dynamics about this reference flight condition, okay? So we can define perturbations in these variables right here. So, like I know x, or wait. Yeah. Shamik says if x star equals t star plus x aerodynamic, won't t star cancel on both sides, and we get x aerodynamic equals minus d. So you're saying that here we are now saying that this new x is aerodynamic, which is what we used to call capital X by itself, but now we're making a distinction. So this is the aerodynamic force plus the thrust, and then this is equal to thrust minus drag. So this is X. So yeah, Shamik, you're exactly right. We would find that X aerodynamic is equal to minus drag in this case. And that makes sense. This makes sense. It's saying that the aerodynamic force acting on this aircraft in the X direction is minus drag. Because, like if we have an aircraft and it's flying at constant altitude with no angle of attack and no pitch angle, then its only velocity will be this u, and that's in the bx direction. And we know that drag drag force would be going this way. Because drag always acts opposite to the relative wind. So I have this. And the definition of X aerodynamic, it's all of the aerodynamic forces acting in the positive BX direction. So that makes sense just from this picture that it would be minus D, because that's drag is the force. It's acting in the minus BX direction. Yeah. That totally makes sense, Shamik. So why do we want an expression for X star rather than just using X sub A? Says UBMAE student. Okay, so the only reason I want to do this is because, let me show you. I can show you the world. Shimmering. Actually, I don't know the rest of the lyrics. I'm trying to find the best. No, I don't want this chapter. Wait, I'll bring you over here so you can see what I'm looking at. It's basically, I'm trying to match convention from textbooks at this point. And okay. Okay, take a look at this equation. So these are the force equations. And this looks very similar to what we have in our notes, but notice there's no thrust term showing here. Actually, maybe I should pull up our notes just to compare it. Where will I find you? Well, maybe. Well, like here it is kind of like expanded out. But you see that we have a thrust term and then we have what we have been calling X. But what I'm saying is this X is only the aerodynamic force, but in most textbooks, they combine these two terms and then they call that X. So if we go back here, you see they don't have a thrust term in that equation. And the reason is the thrust got absorbed in here. And it's one of my pet peeves with these aerodynamics textbooks. Like sometimes you kind of have to like discover that that's what's happening here. And this is going to become more important because now that we're using stability derivatives, I think in the next chapter is what I want to show. Yeah. Like we are deriving this stability derivative today. X sub u, that's the example that we're working on. But this only makes sense if this is the total aerodynamic force. So we'll come back to this. again. Because that stability derivative defined in the table, it all starts with this equation. It's based on this. But this equation only works if this is the total, or if it's the aerodynamic force plus the thrust. This equation is only satisfied if that's the case. All right. So let's take this equation. So we're going to define perturbations because you'll see why I need to do this. Okay, so a perturbation would be defined in this way. Well, the deltas are the perturbations, but if I deviate a little bit from that reference condition, then that's what we call the overall variable x. Or that's how it's related to a perturbation. And then I can do the same thing with the other two. And, okay, drag. What a drag. And what I'm going to do is if you solve for the equilibrium, or if you solve for the asterisk variable from each of these, and then substitute it back up into this equation, we're going to get this. So like x star is x minus delta x. And that's equal to t star, which is t minus delta t. And then minus drag star, which is d minus delta d. So, because the perturbations are small, by definition, that's why they're perturbations, we can write an approximate relationship for this reference flight condition if we ignore the perturbations. So if I say that this is 0, which is, it's an approximation, it's not, these are small numbers, they're not 0. This gives me an approximate relationship t minus d. Okay, so you might be asking yourself, why did I bother? Because up here we have like an equation that's very, very similar. It's x star equals t star minus d star. Why did I go through this bother of blah, 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 doing perturbations to just get an equation that looks very, very similar, if not identical? Okay, the reason we have to do this, these star variables, in this case, they are constants. It's just some fixed number. These are variable. And we're going to start taking partial derivatives, because remember, we want to get the partial derivative of x with respect to u. Well, I wouldn't be able to take the partial of this constant with respect to u, because that thing never changes. Okay. It's a subtle thing, but it is important. So now we're going to dig into the details of this expression and try to derive dx du. Okay, so first, dx du evaluated at the reference flight condition, that's what the asterisk means. It would be dt du minus d drag du. So I'm just taking the partial derivative with respect to u on that equation, evaluating it at the reference flight condition. And then we're going to work on each of these partial derivatives. Well, the first one, we're going to assume that the thrust, as how it changes with airspeed, is approximately 0. This derivative is not 0 in general, especially with jet engines. Like, the thrust capabilities do change with your airspeed. So this is kind of an approximation right here. But the drag is going to be an interesting partial derivative. So what is drag? And how does it change with airspeed? Well, we know drag should increase with airspeed. By definition, drag is 1/2 the density of air times your velocity squared times the drag coefficient times your planeform area. Tim says, a little confused still considering how nominal is not supposed to move. Is the utility here that we acknowledge perturbations in real life and we are finding a derivative of that when it is satisfied perturbations don't knock us off nominal? Well, okay. So, for this reference flight condition, right, we're flying constant altitude, constant speed, just flying straight. Now, in order to accomplish that, I mean, basically this equation is saying in order to accomplish that, what am I saying? X star thrust minus drag let's look at this. And then we're actually saying, sorry, I'm just like going back through here. Is there still a definition also of how big a small perturbation can be before it's considered not a perturbation and simply a deviation? Oh, that's a good question. Okay, hold on a minute. So let's back up. So we were assuming, because I introduced an assumption later on. I said, let's assume that the angle of attack is 0. And okay, if we think about what that means, because earlier I mentioned that the angle of attack is equal to the pitch angle as well. Okay, so that means the pitch angle is 0. Now follow along with me. That would mean that this is 0. So there's no force from the weight acting along the x direction. That makes sense, because if you're just flying with no pitch angle, just level, then all of the weight is directed downward. So that would mean that the thrust plus the aerodynamic force, which we found the aerodynamic force was equal to minus drag. That's what Shamik pointed out. That means to stay at this reference flight condition, thrust minus drag has to cancel. It has to be equal to 0. In other words, it's just whatever drag is being produced, the thrust has to cancel it out so that we keep flying along at constant velocity. Okay, that makes sense. So going back to your question, you were saying I'm confused how the nominal is not supposed to move. So what I mean by that is if I'm flying at constant velocity, I basically have the thrust is going to be equal to the drag, and they should be fixed there. So these values shouldn't change. These are just constants for a given speed. And that's what I mean by they're not supposed to move. Those are just constant numbers. So I can't differentiate those with respect to speed because those are just constants, and you can't differentiate a constant. It would be zero. So I was trying to create an argument so that I turn up with some variables that can potentially change by including like perturbations. But I'm saying that these perturbations are so small that I'm just calling them zero. So basically what I'm saying is that there might be perturbations acting on this aircraft, but like this relationship is pretty much sustained. Is the utility here that we acknowledge perturbations in real life and we are finding a derivative of that so that when it's satisfied, perturbations don't knock us off nominal? Yeah, I guess I'm constructing a situation where the perturbations are so small that they don't knock us off the nominal condition. I think you're right in saying that. And that's why I'm like kind of saying this is approximate here, saying that I do expect that there are little deviations from this. Oh yeah, I keep saying derivative and I'm like, maybe that's a word. And then you're asking, is there a definition of how big a small perturbation can be before? That's, I would say not. There isn't like a cutoff there. It's just that we know that the smaller the perturbations are, it comes back to a Taylor series. The smaller a perturbation is, the more valid a first order Taylor series approximation is. Because notice we're only doing derivatives to the first order. We don't go any higher. And that means we're ignoring higher order derivatives. And you can only ignore higher order derivatives if the perturbations are really small. So you would say they're small enough so that I'm justified in ignoring those terms. But even that's a little hand wavy. Let's be real. Goodness gracious, what the heck am I even doing here? This is a Taylor series in a sense. Yes, sir. I just figured out where I was for a second. Okay, we're differentiating drag with respect to speed and evaluating it at the reference flight condition. So this is drag. Well, the whole term is drag, but this first term we call it Q, which is, that's what dynamic pressure is. 1/2 the density of air times your velocity squared. This is coefficient of drag, and what I want to point out is the coefficient of drag can change with your airspeed. It's not a constant. It's not a constant. And S is the plane form area in this case. So the projected area of the wings and the connecting fuselage. Okay, so if we differentiate the drag with respect to U, we're going to get rho U, coefficient of drag, Oh, wait. Let's not do it that way. Because we have two terms in here that are a function of u. I want to do it this way. I want to say dq du, okay, times cd times s. So we're doing like a product rule here. So then I'm going to hold q constant and differentiate the coefficient of drag with respect to u. And then we have to evaluate this whole thing at the reference flight condition. So this would be, if we just break this down a little bit, it'd be dq du at the reference flight condition, the coefficient of drag at the reference flight condition, the plane form area, which we don't have to put an asterisk because that's not going to change regardless of the flight condition. Q can change with the flight condition. Du. And then S. And let's make a little note here. Q at the reference flight condition. Well, if we look up here at what Q is, it's this. We know that for this reference flight condition, V and W are 0. So this is going to be 1/2 rho U star squared. That's what Q star is. And while we're looking at Q, we will take the derivative of Q with respect to U. Let's do that on the next line. That'll just be rho times U star. And then let's carry over these terms. Okay, now I'm going to introduce an interesting thing that we do by convention. So when they take the derivative of the coefficient of drag with respect to u, there's because the coefficient of drag is non-dimensional, right? But if I take this derivative with respect to u, now I'm dividing it by a velocity, and overall this partial derivative would be non-dimensional because it's a dimensionless number divided by something dimensional. So what they like to do is make a dimensionless partial derivative. So follow me, this is a little weird. They like to instead take the derivative of a non-dimensional term with respect to a non-dimensional velocity, which is defined as u divided by the nominal velocity. You see what I did there? So instead of differentiating with respect to u, I'm differentiating with respect to this dimensionless velocity, which is u divided by u star. But in order to do this, you've introduced this 1 over u star term. And so we're dividing by 1 over u star. I have to multiply this by 1 over u star so that the effect of doing that cancels out. I know, it's a little weird. So, to make this a little more clear, u over u star, this is equal to dcd. Let's scoot this over a little bit. Oh no, let's just start over. It's equal to dcd du times 1 over u star. So yeah, when you see this term, just imagine it as this. And because I'm multiplying it by 1 over u star, I need to multiply this on the outside to cancel with that term and preserve the original expression up above. I know, a little weird, but that's what they do in convention, so we need to do it. Okay, and it's multiplied by s. Okay. So we're marching towards an expression that they get in the table of our textbook. So this rho times u star, we're going to write it in terms of q star. So this is actually 2 times q star divided by u. So this expression right here, if you were to write it in terms of q star, it would be this. Okay, then we got to multiply by this coefficient of drag, multiply by s. And then we have our other term plus q star. And then we have this 1 over u that we needed to add. And then they have a special name for this term. It's c, the coefficient of drag, but with a subscript u. So this term in the green is this, which is the same as this. And the whole point of that, like I said at the beginning, they wanted to make that partial derivative dimensionless. So they had to like divide by this term. Okay. And then we multiply this by s. Okay. So now we've done a bunch of manipulation to get an expression for the derivative of the drag with respect to u. And it is q star. So now I'm going to like gather some terms because they each have q star in common. They have s in common. They're both divided by u. So I'm going to have 2 coefficient of drag times, oh wait, I don't have to have s anymore. And then plus c d u. I'm going to put a box around this guy. Boom. All right, now lest we forget what we're doing here, we're trying to get this term, dx du. And we said this term was 0, and then we just solve for this term right here. So dx du is the minus of what we just got. So minus oh, and we are almost done. Okay, so finally, the stability derivative, xu, all the way at the beginning we defined it as this. It's 1 over m times dx du evaluated at our straight reference flight condition. So it's going to be this same expression, but we have a mass term. Whew. Okay, now this is the cool thing. If you now look in the Nelson textbook, you will see that exact same expression in there. Except in the Nelson textbook, they don't give you any clue as to how it is derived. You just have to accept it. But now, we have shown where it actually comes from. But we're not going to use more class time to derive like all of these ones. But if you do ever need to derive them, you've seen the process once. Like the rest of these, you see like the terms are kind of similar and the process is pretty much the same. So this table 4.2, there's actually like a couple more rows to this table. They show all of these terms. Now the cool thing about this is for common aircraft, you can look up like these kinds of terms and substitute it in, and then you'll get a number for these that you can substitute into the model we derived last time. So I think what we're going to do on Wednesday is we're finally going to apply some of these things. Like I want to find some numbers for common aircraft to plug in and do some analysis of those dynamics. Okay, on the top you used X subscript U, and here you just used delta equals, and here you just used equals. So this means that the stability of the X force is based on the drag coefficient and the velocity. Oh, so are you, Dilly, are you kind of asking like, why do we call it a stability derivative? Does it actually, because like when we talk dynamics, when we say stable, we mean like, is this stable? Is this unstable? Is that what you're asking? Okay, at the top. Yeah, what does this physically represent? Okay, now when it says stability, it doesn't really mean stability in the sense of dynamic systems, I don't think. Like, for example, if this term... Actually... Hold on a minute. I think you could... So this term is what we're going to substitute into our A matrix right here. Now we know the stability of a system is based upon the eigenvalues of the A matrix. So if we plug in numbers for all of these and we calculate the eigenvalues of the A matrix, we're going to find that this matrix is stable if every eigenvalue has a negative real part. So the stability derivatives do play into the overall stability of the system in that the eigenvalues of the matrix depend on this. Now, I think there are rules for some of these stability derivatives, like if this stability derivative has a certain sign, then the eigenvalues of the matrix will be unstable. So I think there is a relationship between these and stability. However, the way you think, I think the way you should think of stability derivatives is like a sensitivity. So X sub U, you should think of that as the sensitivity of the aerodynamic force to your longitudinal airspeed. All right, so If this aerodynamic force changes a lot with airspeed, that's what I'm saying it'll give you. Like, it'll say, it gives you an indication of if that force will change a lot if I change my airspeed. So I think if you have an aircraft that is very aerodynamic, it'll probably have a small value for this because the force won't change as much depending on your speed if it's very aerodynamic. Dilly says, so it's more like a coefficient that relates the change in speed to the aerodynamic forces. Exactly. Okay, Tim, getting back to your question. At the top you used XU delta equals, and here you just used equals. Did I? Oh, I see what you mean. So, yeah, this just means defined as. And since I guess I've already established this definition, part of why I use this notation is for some variables that we use in this class, the subscript u just means you take the partial derivative with respect for u. So this stability derivative is like a little bit weird because it doesn't just mean the partial with respect to u. It means the partial with respect to u, but multiplied by 1 over m. So that's why I'm putting this like defined as here, because it's kind of a weird definition. So it's not just given. Oh, I thought delta. Oh, gotcha. Okay. Yeah. No, thanks for pointing that out. Yeah, so this is how you derive these stability derivatives found in the table. Some of them, these are kind of like Pokemon. And what I mean is every stability derivative, some of them you can derive in a similar way, but for others, it's like there's special tricks that you have to use. And so it's kind of like you have to take a different approach for different ones. And there's weird conventions that you see. I mean, there's patterns. Like if you derive a couple of these, I think you could very easily derive all of them. But I mean, something like this term right here, where you take the partial with respect to a non-dimensional velocity. It's like, what? So you have to like get familiar with the convention that people use for each of these, and what do these terms mean? That's why I say aerodynamics is kind of like Pokemon, because you just have to remember all these creatures that have different definitions. That's part of what makes it really difficult. Okay. So I said this would be shorter, and we actually ran up until the usual time. But we had some awesome discussions. So I hope you're not upset about it. I really enjoyed talking with Tim, Dilly, Shamik, and having a discussion with everybody about the exam and what you felt about it and how we can improve that. So I appreciate all your feedback, guys. Speaking of Pokemon, have you guys played Pokemon Shield and Sword? I haven't, but I'm like, should I get into it? I don't know. Had to get back on the synchronous schedule. The chat is too nice. Hey. Yeah, that's why I love doing this on Twitch. It's great for me too, to try to get a beat on where everybody is. Like, are we on the same page about different topics, the way things are being done. Like it just. So I really appreciate you guys showing up, participating synchronously. I hope it's good for you. I hope it establishes some rhythm for your week. With COVID and all that, it like eliminates a lot of the weekly structure, but I think we need structure to like stay on top of things. It's structure's like a safety net that helps you stay on top of things. So it's helpful for me too to be like, look, Monday, Wednesday, Friday, 3 p.m. We got to be ready to go. Haven't played Pokemon in a while, personally. Yeah, the last version I played was Pokemon Silver. And then I haven't touched it since. But I heard Pokemon Sword and Shield is possibly the best Pokemon game ever. My favorite is Generation 3, personally. What was Generation 3? Pokemon Generation 3. Oh, Pokemon Ruby and Sapphire? There's 8 generations? What? What? So I guess I stopped at Generation 2. I mean, I used to know the original 150, okay? And then Silver and Gold, I probably knew however many there was at that time. Generation 3. Generation 8? How many freaking Pokemon are there now? $896. Where's Mew? All right, my friends. I think I'm going to sign out. Mew is, number 151. My favorite Pokemon was Gengar in the Pokemon Yellow days. Yeah, see you guys. Thanks for being awesome students. I appreciate you. See you soon.